Welcome to this session on amplitude, period, and reflection. And one of the things it covers is to, again, put in x of 0, pi over 2, pi, 3 pi over 2, and so on. I'm not going to do that here because I did that in the previous section, so I'm not going to do it point-wise, but I'm just going to use the graphing calculator and graph it that way. So let's start out with the amplitude. We have y equals a sine bx, or of course we have y equals a times cosine bx. The b will come in soon here for the period, and then we have the amplitude a in absolute value. I will mention that in a few minutes as well, what that means. And then period equals 2 pi over b, or it's b equals 2 pi over the period. Okay, let's start out with the amplitude. The amplitude of the sine cosine functions is governed by the coefficient a that precedes the function. All of the other trigonometric functions also may have a coefficient a. In that case, it doesn't make sense to call them amplitude. You will see that in a later section where it still has a coefficient a for the tangent and the cosecant and so on, but we really can't talk about amplitude there. Okay, so let's have a few examples here. It says amplitude, graph y equals 2 sine x and y equals sine x, and then graph y equals 1/2 cosine x and y equals cosine x. And I'm going to go, I know I already have them here. I had recorded myself previously. I'm doing this again. But I want to go over to the graphing calculator and show you how that is properly graphed. So I'm going to go over there. I will graph them. That was y equals 2 sine x. There we go. I'm going to graph this one. Apparently I go out to 4 pi. I could change this to just 2 pi. Maybe I'll do that. 2 pi. 0 to 2 pi. I would have to be in radians, of course. There we go. So that's 2 times the sine of pi. The normal sine looks like this. Sine of x. There we go. So what the 2 is doing is it stretches the graph in the vertical. That's what the amplitude is doing, of course. Then the other one was 1/2 cosine and cosine. So 0.5 cosine x. There we go. And simply cosine x. And so an amplitude smaller than 1 compared to the original cosine or sine squeezes the amplitude of the function. Okay, I'm going to go back to Word. That was the first example. And that's pretty much what I said right here. Okay, let's look at what a negative exponent means. So here I'm going to go back to a graph calculator. I'm going to graph negative 2 cosine versus 2 cosine. I'm going to start out with the 2 cosine on the graphing calculator. So I'm going to get rid of this one here. I'm going to graph 2 cosine. And it looks like what we expect, starting out at an amplitude of 2. At pi over 2, it goes down to 0, and at pi itself, it goes to negative 2, and it goes back up until at 2 pi, it's back to 2. Okay, what happens when we put a negative in front of that? Well, it simply reflects it around the x-axis, and so it just flips it over. That's all that's to that. Okay, so yeah, that's what the negative exponent did. That's also why this was listed here as the absolute value, so that we wouldn't consider this one here to be the amplitude as -2. We recognize that the amplitude itself is 2. Here it is. Amplitude itself is 2. And the negative here simply means that it's going to be switched around, reflected about the x-axis. Okay. Amplitude is no big deal, so let's move on to something a little bit more involved, the period. The period of a trigonometric function is changed through the coefficient b. It is linked to the function's period by p equals 2 pi over b, or, of course, the other way around, b equals 2 pi over the period. This holds for sine, cosine, cosecant, and secant. So even though I'm not going to cover the cosecant and secant now, but in a later chapter it will still be the same for them as well. For the tangent and the cotangent, it's slightly different. I didn't write it down here, but it's simply the period equals pi over b, or b equals pi over the period. So their tangent and cotangent are somewhat faster. They have a normal period of pi rather than 2 pi that we have for the cosine and sine. But that's what I want to focus on, is the cosine and sine. So let's do that. It says here, graph the following. Y equals sine 1x, b equals 1, and therefore we have a period of 2 pi. Sine equals 2x, therefore b equals 2. Remember earlier I said y equals 8 times sine bx, so the b is 2 here. And when you divide the 2 into 2 pi, right here, actually it's right there. So 2 pi divided by 2 comes out with pi. That's why it says period equals pi here. And then on the other one with a b equals 3, we plug this in here, 2 pi over 3, which is exactly what it says here. And if the b equals pi, well, then we take that pi and we divide. P equals 2 pi over pi, which comes out with p equals 2. We will see what happens with these nice integer coefficients, and then we have this coefficient of pi. We will see when we graph that. Again, I'm going to do 0 to 2 pi at a time. I'm going to go to the graphing calculator. Okay, got rid of the last one, and now it says sine 1x graph. Okay. And as we can see, we do have a period of 2 pi. If you count these down, I think I put them in increments of pi over 4. So over here we come up with 2 pi. So we have one full period for b equals 1, or one full period being 2 pi, because 2 pi over 1 is 2 pi. Now I'm going to put in there a 2. Sine 2x. There we go. There are indeed more sine waves, twice as many put in here. The period is twice as fast. Instead of a period of having 2 pi, we have a period of pi, but that's due to the coefficient b equals 2. So we have 2 pi divided by 2 equals pi, of course, for the period. And the next one, sine equals 3x. There we go. So here we squeeze 3 such periods, 3 such sine waves into 2 pi. So you can consider those numbers getting larger to make the curve faster or make the period shorter. So you get more sine waves in the same space. I'm going to change the window setting to integer numbers, like this, before I graph the next one. So here we have at 1. Notice that this one here is just beyond 3, so the first at 3.14, and the last one here is just beyond 6, so that's 6.28. Just to show you what happens when we don't put an integer number in here, for b, but we put the pi in there. Well, now we expect to have a period of 2 pi over pi, which is 2. So watch. Right there, 2, 4, 6. So this case with a with the b being a multiple of pi or a fraction of pi, we come up with integer numbers for the period or nice fractions, rather than the other way around as the first few graphs were. Okay, I'm going to go back here. What I have written here, well, that's kind of what I said. A large coefficient b makes the function faster, as seen on the first 3 graphs. The scale was pi over 6 or 30 degrees. I believe those are the ones that I have right here. The ones I just did was actually pi over 4. No big deal. The scale on the 4th graph is switched to 1. Well, that's what I showed you in just a moment. So that the x-intercepts show up as 0, 1, 2, 3, 4, 5, 6. That's what you saw. Okay, let's graph a little bit more. Let's see what happens when we have fractions. Of course, we would expect that now the graph is going to be drawn out. So I'm going to do as follows: cosine of x, cosine 1/2 x, which gives us a b of 1/2. And then we divide 1/2 into 2 pi. So we have p equals 2 pi divided by 1/2, which is 4 pi. And then we're going to have 1/3 x, so b equals 1/3, p equals 2 pi over 1/3, which is of course 6 pi. Then we're going to have b equals 5/8 pi, and we divide 5/8 pi into 2 pi. Let me just show the last 2 here how that came about. So that equals originally 2 pi divided by 1/3, and as you can see, that comes out to 6 pi. Here, that would be 2 pi. Okay, that was supposed to be a pi. Two pi divided by 5/8 pi. So of course the pi's cancel, but then you have 2 divided by 5/8, which is the same as 16 over 5. So that's where the period comes from. That's how it's calculated. This is what we would expect from what we saw in the last example. A small coefficient b makes the function slower, as seen on the first 3 graphs. Again, I believe when I do this on my graph calculator, I will actually have a scale of pi over 4. Doesn't really matter. And the scale of the last one is switched to 1, so that the period, we will see, looks kind of nicely there, a fraction of integer numbers. Okay, let's go over there and do that. Okay. So the first one we have is simply cosine x. There we go. Oh, I meant to switch the window back to pi over 4. The scale, that is. There we go. Pi over 4, there was 3 pi over 2 right here, and then we're back to 2 pi. Now I'm going to put in cosine of 1/2 x. So cosine 0.5x. Graph that, and notice that it becomes much more stretched out. I would have to go to twice the width of the screen here to accommodate one whole cosine wave. Okay, then I'm going to go to cosine equals 1/3 times x. This time I'm going to do this exact rather than 0.33. And it would come out even longer. We would have to go to 3 times the window size here, because now the period is not 2 pi anymore, but it's 6 pi. So we would have to go all the way to 18 point something. Okay, on the last one, I'm going to switch this here to, let's see, 1, a scale of 1. And then I'm going to go over here, and now I'm going to put in, it says 5/8 times pi times x. There we go. Graph this one. And 3.2 and 6.4, almost just short of it. 3.2 because 16/5 is 3.2 for the period. So we're able to squeeze almost 2 in here. Notice that the 5/8 for the b is a value that is smaller than 1, I believe. Is it? No, I'm sorry. It's larger than 1. It's almost 2. That's why we come up with a period that is half of 2 pi. Okay. Well, this down here is what I had also explained. Also, an integer or fraction of b keeps the period p as a multiple or fraction of pi. We went over this here, while b being a multiplier of pi itself makes p an integer or a fraction. I had mentioned that earlier. And with that, we're done with this section on amplitude, period, and reflection.